And hello everyone. My name is David Plaza, and this is Randon. Hello everyone. Today we got another session. Plaza, and this related more. Today we got another session. Underwater explosion related more. Remember that this event is sponsored by Underwater Explosion. SNEMI Student Section here in Ecuador. That this event is sponsored by Facultad de Ingeniería, Ingeniería Marítima y Ciencias del Mar. And today Facultad de Ingeniería, we got a really good Ciencias del Mar professor here. Today we got a really good from Myanmar professor here. I don't know how to pronounce very well his name because can you do it?
Yeah, or yeah, as you prefer.
Okay, but we can call him Yeye because one fact about Myanmar, they only have one name. They don't have last name. This is only one name, but it's kind of long. So that is why it's a little difficult sometimes to pronounce. And most of my friends, they change their name for another European name or some kind of a minimum name of their whole name, right?
Yeah, nickname, or you can say.
JJ is from Myanmar, and he studied at the Master of ENship like me. He is a senior about this program. And after that, he decided to study his doctorate in University of Icon. Don't ask me how that means because it's in French, and for me it's difficult to pronounce. But he is really a really outstanding guy working in this field. Now he can present himself and do your work. The room is yours.
Thank you, David. David is a good colleague of mine, colleague and friend. Also, he did the internship, so we can say that we were together, like when he studied in France. So it's a city called Nantes. So I have shown this in the map. So we are in the city at the west of France. So let me introduce my name again. It's pronounced as Pyae SONE OO. So, and I work in the ECAM Institute. So it's a private institute. It's a Catholic institute. So I didn't put a long name. So it's a Catholic Institute of Art and Walk. So you can translate like this. And so there are a lot of sites. I mean, a lot of campuses of ECAM. So 7 in total in France. And there is one in Quito. We collaborated with one of the ECAM, and we have some exchange students from France to Quito. So we have another private institution in Quito. So this is a really nice opportunity to introduce ECAM and also at the same time to present my research work. So the research is, although I work in the EM, so it's the long form is Génie Civil et Mécanique. So it's a civil and mechanical engineering research. It's a national research team, research laboratory in France. So I will introduce more as I explain along. So this is the topic. I guess that you have already been introduced about these topics before, maybe advertised. So it's about the development of the analytical formulations in the field of the underwater explosion. So this is what I have studied during my doctoral studies. So I'm happy to present you about this. So here a little picture of the school that I'm working. So continue just a little bit about some of the partners and the name of the project. So it's a French collab. Yes.
Are you sharing something? Because I don't see. Are you showing something in the screen?
Yes. You don't see anything.
It's not already shown. That is why we are.
Okay. Okay. You could have. Okay. I'm sorry. I thought it's already shared. So is it okay now?
Yes, it's okay.
Okay. So here, this is what I am showing. Hope you can, yeah, you can see now. Yeah. Okay. Okay. So this is a little map that I was talking about. So north at the west. So here is a map of France, and then we are in the west. In the west, so it's a city called Nantes, and then we have ECAM. So there is a little beautiful picture of my institute. And this is the name of the laboratory. It's the DEM, so Civil and Mechanic. So it's a mechanical and civil engineering research. So, okay, I will continue. So let me know if there is any problem. So in the second slide, I would like to share a little bit on who are our partners, what is the project, who are our collaborations. So just to have some idea. So we have Multiplast. So it's a shipyard. So it's a shipyard close to Nantes. And we also have Mecca. It's a design office. It's also based in Nantes. And also we have ECAM. So my institute is also in Nantes. And we have another research laboratory in Toulouse. So mainly we have their collaborations. It's mainly to do the experiments. So we have not yet done the experiments on the explosions. I will show you later. We have some experiments we have done mainly on the impact tests, because these are the institutes, and Toulouse is very famous for the aero industries. So they have these something like a gas can impact test and something like a part strike. And we use some of their experimental findings in my research. So the name of the project, we call it SEX. So now it's a SEX Plus. So it's a continuation of the previous project, the project from my doctoral studies. So I started in 2017. So I forgot to put the date. I finished in 2020. So 3 years. And we work with the French Navy. So it's called TGA. So AIT TGA. And then we have all these partners that I have explained earlier. Okay, so to continue, what is the underwater explosion? So just to give you, so this is the visual image. So this is the one of the, I would say, shock fire test. So we call this non-contact case because it is not about the torpedo or a rocket impacting the ship, but it is more about the explosion somewhere else. And then we have these pressure wave come in to the ship, and then sometimes can be dangerous because it could invalidate your engines. So this sort of studies, and the main interest is to study the dynamic behavior of the composite structure. So we are mainly focusing on the composites. We really would like to study because for steel, they know quite well. I mean, the French Navy, they built many submarines and they have pretty much experience in constructing with the steel, but composites is relatively new. Maybe for the aero industry, they know, but for the naval industries, it's relatively new, we could say. And then there is another problem, which is called hydrodynamic slamming impacts. So slamming, when you have, when you have these power, going out, and then you hit the water, so you enter this water again. So this sort of problem. And so for my presentation, I focus only on the underwater explosion, so to limit the scope. And we have some of the practical application structure, so something like the sonar dome, like this, or underwater ROV, so remotely operated vehicle, something like this. And when you have a mine, and then when it explodes, you could have the damage to your robot. So we will see. And regarding the methodologies, we have so three main methods. Okay. So as everybody knows, first we have these experimental ways to study how is it the explosion. So for example, this is one of the tests a couple of years ago. In Toulon, so it's in the city, more in the south. It's one of the base of the French Navy. They have these, I would say, tonic basin. So it's tonic basin. It means a pool, and you put the explosives and then you explode. And they use this sort of structural setup. So this is a main frame, and they hold the structure, and then you have this effect of the explosion. I will show you the schematics here. So you have this frame here. So the frame, and then you have these plates. So this is one of the plates. So you can test, for example, 3 different plates simultaneously like this. Just to, for example, if you want to understand the directional effects of the explosion. So when you are directly under the charge, or if you are something a little bit, some angles from the charge, and to understand. And so you have the target plate. So the plate is a circular shape, but it can be, you can use any material you like, aluminum, steel, or composites. So composites in our case, it's carbon fiber epoxy or glass fiber epoxy. So this is the main material that we would like to study. And we have this explosive charge, and then these are the submerged frame. Usually, sometimes we hang it, or sometimes it floats. So with the natural buoyancy point. So, and then there is air behind the plate. So it's more of you have water on one side, and then you have the explosion, the wave, and then you have air on the other side. And then you can see maybe, I don't think there is a camera here, but the observe using the strain gauge. And sometimes you can measure the plastic deformation. So, and there is also some sort of test. We don't have it in France, but this is one of the photos from United States. So in 2015, so in China, in United States, I think in Australia, they have these sort of facilities. So they try to mimic the shock wave of the explosion. So I will show you later how is it like that in some sort of like the plot, So for now, these are the sort of facilities we use in order to understand. So the advantage of using this sort of setup is you are working in the smaller scale, so it's less expensive than this sort of, like a pool. And also you are in more control way, so less dangerous, because you don't need to deal with the real explosives. So for example, you have this pressure tank, and then you have some sort of like a diaphragm, and then you increase the pressure. At some point, the diaphragm will break at some pressure, and then there is something called a projectile. So somewhere inside the gas barrel, and then when the valve break, the projectile will go all along the gas barrel, and then it will hit a water chamber. So we have some sort of I don't know, some rubber or something, and when it hits this diaphragm, it will generate a shock wave. So it's more of a one-dimensional propagation of wave. So it's not exactly the same, but this is another way of trying to mimic the wave, the loading from the explosion. So this is more realistic in a real explosive setting. But this way, there are some advantages. For example, you can set up something like a camera, a very high speed camera, and then you can see all the deformation stages. And then if you use something like a chamber which is transparent, you can even see how is it like the shock wave and how is it the interaction, and then the cavitation and a lot of things. So many interesting ideas around there. So this is just to give you an idea about how we study these sort of fluid structure interactions. So let's go to the second method that we use to study this sort of explosion. So the second method we call this numerical. I am sure everybody knows. We use finite elements, and then there are a couple of different ways. So many different ways. So here I try to limit. So I limit my scope, what I have studied during my doctoral studies. So it's not. Otherwise, it will be a lot of tools, a lot of numerical setup to study these sort of explosions. So here, what we can do is you can calculate, okay, what is the pressure? I will show you the equations later. What is the pressure? And then you can calculate the equivalent impulsive velocity. So this is a very, very easy way to try to do this, because you can model just a structure. You impose the impulsive velocity on the shear element, and then you study. So this is just an initial value problem, and very, very quick, but I will show you the results later. This sort of approach is not always very sufficient. It is very fast, but there are some discrepancies. There are some differences when you compare to the experimental results. So the second sort of tool is called LS-DINA. So I use LS-DINA a lot. So it's a nonlinear commercial finite element tool. You can also try with Abacus or Patron maybe not very Patron maybe not very efficient when it comes to dynamic, but you can use Abacus, for example. And LS-DINA becomes the same as ANSYS right now, because they brought it back. So, and the letter like USA, it means underwater shock analysis. So it's a special extension of, I would say, LS-DINA. Normally we don't have access, so you have to request the access from the I would say the military, or you need special permission and you need special license to use this tool. So can be sometimes quite administratively complicated. Okay, so that's to give you. So not everybody have access to this tool. And so the second, so just to go back, the second part of the approach is the boundary element approach. So we don't have any more fluids, just a structure, but we have this boundary. So maybe some of you might know what is the boundary element calculations. Okay, we don't really use the fluid elements, but at this boundary, we treat that there is something like a membrane of a fluid, encompassing the structure. So there is a structure. We don't have a real fluid. Why? Because to include the real fluid, it would take a lot of time, and then it is very difficult. So it is not fully coupled, but it is something like a semi-coupled approach. So the first approach is completely uncoupled. We calculate the equivalent velocity, and then we impose it to see, okay, what is the effect? Very fast. Second approach, also very fast, but you need a special permission from the special tool. And so you use this tool. I will need to explain what is Pyae later on. It's a doubly asymptotic. For now, it's not important. We have this boundary, and this boundary will treat as if it's a fluid. Okay, and you can calculate what is the explosion, what is the pressure, and then it will take care automatically about the interaction between fluid and structure, even though we don't really model the fluid. Okay, this is really important. We don't have any fluid here. And then the last part, by the way, I only show something like a quarter of a circle because I show you we want to study about the circular plate, but if it is symmetric, if the explosive charge is directly like you are, for example, the explosive charge somewhere under, and then you have this plate, and then you don't need to worry about the asymmetric effect. Maybe in reality there might be, but in the simulation this is completely perfect, completely ideal, and then load-in will be symmetric load-in. So the deformation symmetric, so you don't really need to model the whole complete plate, just a quarter is sufficient. And then you apply the symmetric boundary condition here and here on the edge. And then here is something like a simply supported condition. You can try clamp boundary also. You can try many things. It's very fast. And then the last approach, you model also the fluid. But it is not the real fluid elements. Real fluid elements, I mean, the fluid elements which we use in the CFD software, but it is really expensive. So we are using something or another special. We have a lot of special tricks to save the time. But then what about the reliability? I will show you in a couple of minutes later when I compare all these results with the experimental results. Okay, so but we have a lot of tricks, and then it takes a lot of time like to model this problem. Even though you see it's only a circle, it's only a plate, but it can be really difficult. And then the final approach, which is also my thesis, it's about the analytical development. So analytical development means so numerical, numerical tools are like always generic, like always general. You have these sort of equations, and I don't want to repeat all these. How is it about this numerical approach? But analytical tools, they are mainly comes from the first principles. So first principle, something called a physical sense. So they comes from some physics, some geometry, and then you derive the equations according to these. You have governing equations, you have boundary conditions, you have an initial condition. So you have the partial differential equation, you solve it. And then you have the final equation to solve. So something like this. It's very easy, not so easy to derive, but it's very easy to implement it in some programming tool like MATLAB, for example, or Python. So here is one of the plastic deformation. So there is a formation of the cylinder. You have an explosive charge, and you have a plastic deformation. So all these form, you model it. So this is not exactly my research. This is one of my predecessors, so the one before me, but working in the same laboratory. So he developed a cylinder. So he represented cylinder as a plastic string which is resting on the plastic foundations. So okay, I will skip the details. It's otherwise it will be too complicated. Or if you have any questions, you can contact me, or you can also if you are interested, you can at the end I will show you my contact, and you can contact me, or you can find my articles. So there are some published articles already, and then you can read, and then you can explore more. Okay, so here is just some introduction. So this is more or less the same as I have shown, but more analytical. So he calculates equivalent impulsive velocity, and then he imposes it on the cylinder. And then for the deformation, he used this sort of plastic string resting on the plastic foundation. Why? Because cylinder, you can imagine when it's deformed, and the equations can be very complicated. And so by assuming that it is just a string is a one-dimensional element, so you simplify the dimensions of the problem. Otherwise, you are gonna have to deal with 3 dimensions. It can be complicated. So you reduce the dimensions by supposing that it is only 1 dimension. And so the spring represents one of the bending stiffness, and then spring represents something like a extensional stiffness. So Okay, this is pretty much detailed enough. So I will go to the second development, which is so the figure on the top, it is my development during my PhD on the plate. So first I started with just a plate with a spring at the back, and then you have water. So I should have put so the explosion is coming from the left. You can see there is a pressure, and then the plate will go into the direction of the spring, and then the spring will resist. So the spring is an equivalent of a bending stiffness of a 2D plate. Okay, you have to understand a little bit on the how is it in the plate theory. Okay, so this is a simplified version of modeling. So it's only plate and the spring. So it's a mass spring system. So very easy to solve. And by using this sort of things, you can also see how is it. But usually this is not sufficient. So you, in the end, you really need to use something like a plate theory, which I will show you later how I did that. So, and then the last thing of my development is a cylinder. This is basically the same thing, but what is different with the cylinder on the left? The cylinder on the left is a steel cylinder, so it's more of a plastic deformation, and then you have a very strong explosion. Here, we are assuming that we have a very weak explosion, and then we started something like elastic deformation, but you will see that it's complicated enough also. And so why, so these are, I would like to like repeat again, like why we are developing analytical, because you can see numerical, everybody is doing this, but then you have to remember that it can be computationally expensive. It means it takes a lot of hours, many hours. Sometimes we don't want that. We want some results really fast, and then it is complicated because compared to the analytical tool, numerical is much more complicated because you have to set up your model. Not only the modeling, you need to know the parameter, and then you set up all these parameters, and then you need also have enough experience and enough knowledge to know what you are expecting, what your results should be. And then when you interpret the results, also it can be challenging. And also I have shown you like this tool for this problem. Sometimes you have these administrative complications. So, and then the analytical, very fast, very simple. Of course, not so easy to derive, but once somebody already develops, for example, there are so many papers, and you can take advantage of that. You can code in some MATLAB or Python, and then you can study so many design studies. So the only drawbacks is sometimes analytical tools, the geometries are really simple geometries, like as you see, plate or square, rectangular plate, circular plate, you see a cylinder. Okay, so now a little bit of basics. So we have the explosion. So we got this is an exothermic chemical reaction. It's really unstable compound. So you imagine you have explosion. Okay, boom, and then there is a shock wave. There are so many aspects. I will show you another slide later, you will see. But first of all, when you have explosion, what you need to understand is you have this very unstable compound, okay? And then they release a huge amount of energy. So energy in terms of temperature, so very high temperature, just very hot. And then a huge amount of pressure. So the water immediately around it, they are compressed. And then this compression, they go into another place. So it is like a compression wave going. So at first, the CW is I would say sound speed in water. So at first it is very fast and the pressure very huge. But then the pressure is falling, and how do we know this? The question. So a lot of people already study mainly a lot of developments during the Second World War. In fact, they already started in the First World War, but a lot of documentations, I found this during the Second World War, and they already tested using the pressure transducers, which has already been there around like 1930 and 1940s, 1945, 1950s, and later on they continue to study. Even though we have some sort of treaties, but people study in their own smaller scales. So we know that when the explosion, when we are inside, so we can calculate the radius of the charge. And when we are something like 15 or 20 times the radius, we say it's a near field explosion. Very complicated, very nonlinear. But when we are outside of this range, it becomes a far field explosion. So it is a linear relation, linear in terms of the pressure and the speed of the propagation. Okay, so P equal to rho C, rho is the density of water. C is the speed of sound in water, so around 1,500. And V is the particle speed, or we can say the speed of propagation of the shock wave. So because it's a propagation of the disturbance. Okay, so this is a relation, and you can, if you are interested, you can read the book written by Cole from the Princeton University Press. It's a really famous book. And so in terms of the physical phenomena, you can see that first there is a pressure wave, something like this. I will show you okay, here is the equation. So it's the exponential form. You can really see the exponential form. It's a decreasing exponential form. So it's a negative here. And after that, when you have the explosion, you have this first pressure wave. And then after that, you have this oscillation of the gas bubble. So unfortunately, I didn't have the video, but you can check. It's very easy to find it on the internet. For some people may have already some idea. When you have a very reactive product inside the water, and when it explodes, you also have some sort of residual gas. And then this residual gas, they expand, and then they contract, they expand, they contract. So these are the different phases of this gas bubble. And then when it contracts to the minimum volume, it releases the pressure. It's inversely proportional to the pressure. So every time it goes through the minimum size of the gas, it releases the pressure. But then you can see it makes sense, because first it releases a huge amount of pressure, and then the second phase, the pressure, you can see, is significantly smaller. So this is just a representation. It's not supposed to be not with the values, but when you put the values, we have already seen from the experiment that this sort of figure is approximately true. Okay, so I will continue. There are some other effects also. So this fiber oscillation I have already explained. There are something called local cavitation, reflection. So imagine that you are, for example, inside a detonic tank, and the tank is not so large. So sometimes when the shock wave goes to the let's say the wall of your pool, and then they come back. So these sort of effects. Sometimes when the gas bubble reach the free surface, you can see a dome of it forms a dome. So this is the photo that you have seen. Like you have an explosion. Normally everything's so calm. Like when you see out of the water, because everything's happening inside the water. But sometimes when you see that the explosion, like in some movies, and a lot of gas and going out, and actually this is the gas product reaching the surface and then going out of the surface. Okay, so let's go. So all my studies are limited only to the primary shockwave effect. I will have a master student pretty soon to include the secondary and the tertiary bubble effects, but not yet. at the moment. So everything is limited to the primary shockwave effects. And so these are the comparisons with the experimental results. So it's one of the experiments during the Second World War, again, because there are so many results at that time, mainly by American and British Navy. So one of the experiments I took, so many experiments, so many results. Right now, for the research purpose, they publicize or they publish it, okay, before it's more confidential. Right now, you can find this sort of information. So so this is a plastic deformation, so it's a circular plate. Of course, I have done so many other validations also with the composites, but this study is very interesting. So what you can see here, there are a lot of lines. So it's I am comparing the deflection at the center of the plate, okay? And so this cross here is the experimental result. So they measure the final deflection, which is 30 millimeter, okay, of deformation. And the black line here is the results that you see on the right. So this is the approach with the fluid elements, fluid acoustic elements. And it maps really well. I am not going to go into a very detail. I will explain what is it here. So first you see, just wait a minute, it will come back. So first, here you start to see the effects of the explosion. So the explosive is somewhere below, and then I don't know if you could see it clearly here, because you have the plate, and then you can see here is a zoom figure. You can see the plate is slowly deforming, and then the zone, which is the color blue, represents the area where the pressure is zero. It means that when you have an explosion, you have a very huge shock wave arriving the plate, but then very soon the pressure is decreasing because your plate is moving. So if you push something like a plate, and then if it moves, the pressure, you will see that the pressure decrease. So this is the sort of effect. And then when the pressure decreases up to the point, after some point, you have to imagine the physically. After some point, the water becomes evaporated. So this is what we call cavitation. So up to here is okay, but after here, so here, very soon, 0.03 millisecond, we have a cavitation. And then from this line to 1.7 millisecond, it's the cavitation. So what does it mean? So you have a pressure, and then very suddenly, the water evaporates. So the plates behaves like you have a pressure, you have a shock wave, but the plates behaves like in air, because there is nothing anymore when you have a cavitation. So this is really complicated phenomena. We really would like to understand. We haven't reached that far. Have some publications, but not so advanced yet. So everybody really focusing to understand what happens with the cavitation. Really interesting problem, but really difficult. So this sort of simulation with the fluid, it captures this sort of cavitation phenomenon really well. And that's why you see the final deflection really like matching really well with the experiment. But then the rest of the simulations, these are the simulations. If you remember, so the first is the blue line is the first model as with the equivalent velocity alone. And then this one with the dashed line is the model with a boundary element approach. You see, it's not so perfect, but you can still use. But you have to understand that you might have discrepancy. So that's why it's really complicated to use numerical tools. That you have to know what are their limitations. And then, okay, I will not go into very detail. These are my publications from my publications. So I put some of my publications, also the one that I used to model these analytical, develop this analytical formula. So I also consider something called the geometric nonlinear effects. So the geometric nonlinear effects it's the when you have some sort of like a large deformation. So normally, you know, when you study about, for example, quasi-static, let's say quasi-static, or even dynamic, normally the force and the deformation or acceleration, the force and acceleration of the plate, they are directly proportional, normally. Or maybe some of you have done this, I would say, 3-point bending test. You will see that force and the deformation, you see a graph is really a straight line. But you will reach a certain limit, and then when you pass this limit, you are no longer linear. So that means you have a straight line, but then it is not really a straight line after. Maybe a parabolic, we don't know. So this is why we call nonlinear. But there are so many nonlinear effects, but this is one of the nonlinear effects. We say large nonlinear due to large deformation. And then, so you have a normal equation of motion like this, but then you have one more term which is due to nonlinearity. So I add this term, but you have to go to my publications to really understand these equations. So I will not going to go into very detail. So there are 2 equations here. So the first equation is the equation for the plate, the equation for the structure. Okay, and then you have a second equation. So you have to. So the second equation is the equation for the fluid. And then how do we do when you connect these fluid and the structure? So usually what we do is we use the boundary conditions. So at the interface, so it's the point where the fluid and the structure are touching. At this interface, we impose or we assume that there is a continuity of velocity. So the velocity of the fluid is the same as the velocity of the plate. And then there is a continuity, not continuity, sorry. There is also something called, there is more technical term. We have a kinetic condition and kinematic condition. So kinematic condition is this one. You have a velocity continuity condition. And there is also, we have a pressure condition. It is solved by this equation here. So it's a first order partial differential equations of the pressure at the interface of the fluid and structure. And by using these equations, you can model analytically the fluid interaction due to underwater explosion. I hope, well, not completely clear, but maybe a little bit okay. And the first order shear deformation theory, but I don't want to go into super detail about this. And some results on the simply supported carbon fiber epoxy plate that I use. So there are some of the properties of the material, the loading that I use, or that we intend to use for our case studies. Of course, in my article, I have done some sort of parametric studies as well. So parametric studies means I keep several parameters, but I change one of the parameters, to understand what is the effect. So you can see it's a comparison between my method, analytical, and the result of the numerical tools. So I won't go into so detail on this diagram now. This is just a comparison of the results of the deflection between my tool and the numerical tool to understand. And the numerical tool, we already study what is the effects by using with the experimental results. So something like this. Okay, so the idea is to validate our analytical tool to say, oh, hey, we can use our tool. It's faster and easier. So like this. And this is my current studies. So after studying about the plate, I shift my research more into the cylinder. And so you have to use, so its idea is the same. You have on one side, you have an equation for the cylinder, a little bit more complicated. And then on the other side, you have the equations for the pressure. So maybe, yeah, to save the time, I won't go into very detail. This is the governing equations. It is called modal approach. So you solve it's very common in the vibration studies. You have you have a wave in the, let's say, longitudinal direction, and then you have a wave in the circumferential direction. So it is a letter M and a letter N here. And the modal approach will allow you, so it's a superposition of all these waves, and then when you sum all these, you can plot what is the deflection on any point, anywhere you want. So this is a really fast way to solve this type of problem, but we are only in the beginning. So you can see it's a classical shell theory. So some of you might heard of it. Usually in the beam theory, we call it Euler-Bernoulli. The beam is really easy element, but then you increase the dimensionality. So you have a plate, and then if you want to be complicated more, you have a plate and then you fold it like this. So you have a cylinder. So it's basically the same. And then if you have a curvature on both directions, you have a shell. So these are the evolution. So you can, there are a lot of literatures on this. So, and the idea is really the same, structural equations on one side, so the first one, and then fluid equations on the other side. So these fluid equations, I adapted a method called doubly asymptotic approximation. So this is TAA. So it's a little bit complicated. So, and I compare my results. The straight lines are my results. You can see it's not so good. There are 26% of the relative error. And so right now I am saying in my development of the equations, but by shifting into the different sort of geometry, what I realized is sometimes with the plate, you have an explosive, and if you are far enough, you have a pressure which is more or less uniform. It's okay. What is really complicated is you don't really have the same pressure on the different points of the surface. You can imagine you have an explosive. Here maybe the largest load in, but then maybe if you go to the circumference, the loading is not the same. So we encounter this sort of problem. So I modify. First, if you may remember, the equation is really simple, but because of this, also there is a heavy side function. It's one of the mathematical functions to go 0 and 1. So you have to use this because the pressure form is exponential like this, but you have so many pressure profile, which is not only the same exponential, the same slope, I would say, but also not the same level also. So, and also they don't start at the same time. Sometimes they are 0 and then they stop right away. So you have so many, so these pressure are the pressure plotted on the different points along the circumference of the cylinder. And so when I develop my equations, I need to consider this effect, and it complexifies a little bit. So I call this time delay effect because the waves came in, but not at the same time, but some of them are delayed by the geometry. And these are the equations. So, but the idea is the same, structural equations on one side, and then fluid equations. I have two different models. One model I don't consider, it's called early time model, because I am only considering you have a pressure wave and then you have these interactions due to the radiation. It's a technical term. So, and the second part of the equation is more complicated because you have something called radiation effects, and at the same time you have something called water added mass effect. Water added mass is when you don't have cavitation. By the way, my studies, all of these, I don't consider cavitation. Cavitation is a phenomenon. I explain you with the movie, with a little animation where your pressure becomes 0 and then suddenly you don't have anything. it's very complicated, so I don't consider cavitation. So if the water remain contact with the plate all the time, that means we don't have cavitation. But there is another problem to consider, because if the water is attaching to your plate all the time, and when your plate accelerates, what happens is this water, they accelerate or decelerate together with the plate. And this is called water added mass effect. Some of you might be familiar with when you consider, for example, a ship, when it's moving in water, especially in the motion analysis, you have to consider this sort of water added mass effect or virtual mass effect. So maybe it might ring a bell. And with this effect, I find that for example, my previous results with the blue line, and then when I try with this time delay effect, my results improve really well. Like it matched exactly the same as the numerical too. This is a current up to now. So the general perspective to conclude my presentation is that we really would like to go to study the cavitation. We really would like to include, you see this secondary, tertiary, this parallel position. And also we are still trying to compare for the experimental results for the cylinder. But before I conclude, I would like to show you, like, it's really nice with the analytical tool. So for the thin plate, it means when you take the ratio between the length and the thickness, it's relatively large. Not really a very thin plate. It's a relatively speaking, So it's took about like 2 seconds to solve the equations. But when you use, this column is a boundary element, not bad, 200 seconds, not so long. But when you use something with more precision, when you model these fluid elements, you see that, wow, it's like 3.5 hours. So you can see the big difference between my two here. And the first column here is the termination time. So termination time is something called when you want to finish your calculations. That is, especially if you are doing something called explicit calculations. Explicit calculations mean you are going from one time step to another. You need to define when to stop your simulations. So usually for the implicit, sometimes we do that, but sometimes for the static problem, we don't really care. Okay, but for the dynamic, we need to know when to stop your calculations. So it's be careful with the scale, it's millisecond. Okay, because it's a very fast, happening really quick. And you can compare the time difference. Okay, so for the cylinder, wow, 5 hours. 5 hours with the boundary element approach. I haven't even tried with the fluid elements, which I hope that not be so long. We will try very soon. So I think this is all. So here is my ResearchGate profile. So you can contact me, or you can type my name in the Google. You will see some of my publications. Some of them are free. You can download it if you are like really interested to. And also you can ask me any questions. I'm happy to answer. So thank you. Thank you for your attention.
Thank you, JJ, for my interesting presentation. Sometimes I see so many vibration problems here that I
exactly. Exactly. This is vibration problem also, but a bit more extreme.
Anyone has a question here?
Yes. Please.
Hello, Professor, can you hear me?
Yes.
One quick question. At the beginning of your presentation, you mentioned that you take advantage of the symmetry, right? So you work
Yes.
only with a quarter of that. In
Yes.
some cases, we have we suspect that including the symmetry conditions increases the stiffness. Any comment on that?
So to impose the symmetric boundary conditions, it might increase the stiffness. Usually you should have exactly the same results as a full plate model and the quarter plate model. So for me, in fact, I have done so many simulations. So I have shown only on these quarter plate results because I compare with the full plate results and they are exactly the same. And then because I want to do so many simulations, so maybe when it increase, maybe in certain cases, I am not sure. There
Yeah.
might be.
In some
Maybe yeah.
Yeah, it's possible that in some, as I don't know, maybe it depends on the loading, but it is possible that, for example, if you assume that in one direction you assume that the slope is 0, maybe that would increase the stiffness. But anyway, another thing is that at the end you mentioned that you consider both thin and thick plates. What's the boundary between these two type of problems?
Okay.
In thick, you consider tau in the vertical direction?
Let's go back. Yeah, this is a really interesting question.
Exactly.
Yes. So the last page.
There, exactly. You consider thick and thin.
Yeah.
In the what's the difference in the model? Is that you include in the thick case you include shear stresses?
I include both the shear stresses for both of these models.
Wow.
But the thick plate, the importance of the shear is more.
Yeah.
So because I am considering first order shear deformation theory for both of these models, so that's why I know. But yeah, I have done a lot of tests also. I am staying thin to make it easier to differentiate, but in fact, I should have included the ratio between the length and the thickness of the plate. So the first one is around 60. So length over thickness, and the second one is around around 20. So it's 3 times smaller. It's the same thickness because so thick and thin, it doesn't really mean it is like a huge thickness. No, it's a relative speaking. So the first one is very long, and so even if the thickness is the same, when the plate is really long, you can imagine it's very flexible. It becomes more flexible. And so the stiffness is not the same. And it has a lot of consequences when we talk about the shock wave and the loading, because I was really interested into studying the behavior of the cavitation. So in some cases, we saw that there is cavitation. So the more flexible the plate, the more we have the cavitation. So, but the boundary between thick and thin is, I would say, the relative ratio, but I consider everything for both of these, just to be sure, because we don't really know when the thick and the thin effects, but there are so many effects to consider. For example, shear, for example, but I already included, but maybe for thin plate, maybe I could even remove because it's more like a classical thin plate theory. But anyway, it doesn't really matter because it's super fast. You can see it's 2 seconds, so you can include a little bit complicated to implement, but it's okay. And you know that the effect of shear will be very, very small for the thin plate, but there are some other things which is called nonlinear effects due to large deformation. And for thin plate, it's very, very fast to arrive to the nonlinear state. And for thick plate, if you are really in the elastic domain, you don't really see the nonlinear effects, something like that. But there are so many things. Yeah.
Thank you very much, and congratulations.
Yeah, thank you. So it's an interesting question.
Yeah, I have one question for you.
Sure, go ahead.
Is any possible way that any of our graduate students, or most of them are near to graduate, they can go to the Econ University or try to get a scholarship or something like that, or try to
okay. So yeah, that's also another question in a different perspective, but really nice. So usually, most of the researchers are managed by not by me directly, but by my thesis director. He used to be a thesis director. Now he is my colleague. But because in France there are different levels. So let me clarify. For me, it's an assistant professor. So and then I need to supervise something like 3 PhD students to reach the second tier level. And so LV, so my professor, you can find his name also in my publications. So he is a professor level. So to have this professor, you need a lot of experience. And
it's possible to
but to answer your question, I think yes. But first of all, we need to have. For now, I don't really have any proposals at the moment. To have this proposal, so I don't know how it works in Ecuador, but here it is like a job. So in order to have something like a PhD or postgraduate studies, you need to contact the professor directly, and then he hire you. So they pay you salary. So you pay tax also, so these sort of things. But of course, you have the opportunities. Like you can look at, for example, my researchers, my professor researchers. If you find anything interesting, like you go directly. Also, you can contact me, and I can also talk with my professor and to study his CV and write a cover letter maybe. And
that is important. The cover letter.
If it is relevant, mostly we do a lot of marine related researches. Of course, your Navy school, and you have a naval department, as I see. Yes, so maybe you can try. So, but we don't give scholarship. It's more like a job. So we give salary. So it is not a scholarship here. But to give you some other information, right now I don't really have any proposals yet. In order to have these proposal, we need, for example, finance to pay the salary of the PhD students. And in order to have the finance, we need to apply. And for now, I'm trying, but I need to write something like a proposal, and then we have to submit it to for now it's more of a military related, so we have to submit to the corresponding organization, and then they will decide whether we will have a grant or not. So something like this.
Thank you.
But if we have the grant, yes, well, why not?
But this is only for PhD, but in case of master?
For the master, I don't see anything. So the most we can do is something called MSR. MSR is a Memoir Scientifique de Recherche. It's something like a master thesis. So this is the closest thing to master program, but we don't really give a master program. As far as I can understand, we collaborate with EMship. So it's Erasmus Mundus, but to explain the others, Erasmus Mundus program for ship design, but we don't have any courses here in ECAM. is a private institution. So what we do is we propose some master thesis.
You can help us with one cover letter for one student for the master to enter to the ENship.
For also yes, it's or even you could help we know, but EMship right now I think there are a lot of applicants. So what I can see here is
that
really
is why the cover letter is very important at that time.
Really competitive right now. But yeah, but why not? Because EMship, they accept a lot of people from Ecuador. They already know. And then Jonathan, Priscilla, they are already working in University of Liège and helping with the program. So why not? You have a lot of chance, and they know Ecuador. They know the people there. So yes. And for ECAM, it's a little bit more complicated. So at the moment, the most we do is we propose some master thesis program to EMship, and then you have to pick it up, and then later on we propose PhD thesis.
Okay.
Yeah.
Okay, yeah.
Hope it's clear.
Thank you again for this meeting.
Thank you too. So I will stop sharing the screen. So I hope it's clear. Maybe some benefits to you.
By the way, I would like to invite you here in Ecuador sometimes, in any case you want to come.
Yeah, I would love to. It's a really nice country. And
yeah, it's a very nice country and really good food here.
Yeah, so would be happy to visit sometime in the future. We will see.
Okay, thank you.
Yeah, thank you too. So
goodbye to Yaya, please.
Okay, bye. So have a nice day. I think it's a daytime there.
Yes, it's almost 12 o'clock.
It's more here is evening, so it's around 6:45. So I need to go back.
Goodbye.
Okay, bye. So I will disconnect.